As large language models grow, we face a fundamental physics crisis, a direct trade-off between capability and computation. Training and running a trillion-parameter dense model requires unfathomable compute power, threatening to melt silicon and bankrupt enterprises. But what if we could scale a model's knowledge capacity to hundreds of billions of parameters while keeping its computational footprint constant? This is the core genius of Mixture of Experts, or MoE. Today, we will explore MoE routing, the high-performance dispatching algorithm that powers modern models like Mixtral and DeepSeek. In a traditional dense neural network, every single token must pass through every single weight parameter in the model. If a model has 80 billion parameters, then every word generated requires 80 billion active flops. This is the dense scaling trap. Expanding model capability requires increasing active parameters, which directly raises compute latency, hardware costs, and energy requirements. To break this linear relationship, we must transition from dense compute to sparse compute, activating only the precise neural pathways we need for each specific token. A sparse mixture of experts network replaces the standard dense feed-forward layer with a set of parallel subnetworks called experts. For instance, a model might have 8, 16, or even 256 experts. Crucially, each individual expert is a standard, compact neural network. When a token enters the MoE layer, it doesn't visit all experts. Instead, it is dynamically routed to a tiny fraction of them, typically just the top 1 or top 2 experts. By doing this, we keep the total active parameters per token extremely low, even as the total model capacity grows massive. At the heart of this sparse architecture is the gating network, or the router. The router is a simple, lightweight linear layer that takes a token's hidden representation and decides which experts are best equipped to process it. It computes a numerical routing score for each expert by performing a matrix multiplication between the token's representation and a learned routing weight matrix. This produces a vector of raw logits, one for each expert, representing the token's affinity for that specific specialist. To enforce sparsity, we apply a Top-K selection on the routing logits. If we are using a top-2 gating strategy, we identify the 2 experts with the highest raw routing scores, set the scores of all other experts to negative infinity, and apply the softmax function over the remaining values. This produces a sparse gating vector where only the 2 chosen experts have non-zero probabilities, while the rest are 0. This gating vector acts as a set of dynamic blending weights, determining how much influence each selected expert has on the final output. But training such a routing mechanism is notoriously unstable. Left to its own devices, a router is prone to a catastrophic failure mode known as routing collapse. Early in training, a single expert might perform slightly better than the others. The router, seeking to minimize loss, begins sending more tokens to this expert. This expert gets more gradient updates, making it even better, which causes the router to send even more tokens. Soon, all tokens are routed to a single expert, reducing the model back to a small, under-capacity dense model, while leaving other experts completely untrained and idle. To prevent routing collapse, researchers introduce an auxiliary load balancing loss during training. This loss functions as a mathematical penalty for uneven token distribution. It is calculated by taking the dot product of 2 vectors, the fraction of tokens actually routed to each expert in a batch, and the average routing probability assigned to each expert across that same batch. By minimizing this load balancing loss, we force the router to distribute tokens evenly, ensuring that all experts are utilized and trained to their full capacity. In hardware implementations, dynamic routing presents a massive engineering challenge. GPU parallelization requires static tensor shapes. If different experts receive vastly different numbers of tokens, we cannot execute them efficiently in parallel. To solve this, models define an expert capacity limit. the maximum number of tokens a single expert can process in a forward pass. If too few tokens are routed to an expert, its input tensor is padded with zeros. If too many tokens are sent, the excess tokens are dropped entirely, bypassing the expert via a residual connection. This maintains stable GPU execution times. The results of this engineering masterstroke are revolutionary. Take Mixtral 8x7 billion, for example. It possesses 47 billion total parameters, but activates only 13 billion parameters per token. This allows it to deliver the latency and speed of a 13 billion parameter model while matching or exceeding the accuracy and quality of a 47 billion parameter dense giant. By separating total parameter capacity from active computational cost, Mixture of Experts pushes the boundaries of what is possible in modern AI. Mixture of Experts proves that intelligence doesn't require brute force scale. By organizing parameters into specialized units and using a smart routing layer to dynamic dispatch work, we can build models that are both incredibly smart and computationally elegant. If you want to master the mathematical and hardware innovations of deep learning, hit the subscribe button for Gemini 3.5 Flash model. Let's build the future of AI, one optimal routing decision at a time.